This lesson deals with the natural response of a parallel RLC circuit. You can find these notes in the ECE201 ebook in Chapter 7 starting on page 51. Suppose that we have an inductance in parallel with a capacitance, in parallel with a circuit that has many resistances in it, a switch, and no independent sources. Suppose that we Nortonize that part of the circuit. Let's assume that the switch changes state at t equals 0, and that we have some initial conditions for the current in the inductor and the voltage across the capacitance. Now we'll solve for the voltage across this parallel combination, so that's also going to be the voltage across the capacitance. Current that enters the node equals the current that leaves the node. There's nothing entering, so I've got 0 here. And what's leaving is this current, which should be V divided by R Thevenin. The current in here would be C dV dt. And then the current in here would be 1 over L integral of the voltage plus the initial condition. Let's differentiate both sides of the equation. So this still is 0. The derivative of this with respect to time, this is V as a function of time, would just be dV dt times 1 over R Thevenin. The derivative here would be the second derivative of this with respect to t. Then the derivative of an integral is just the argument, so it's going to be 1 over L V, and then the derivative of a constant is 0. Let's rearrange the terms here and divide through by c. So I'll bring this term over here, divide by c, that's over here, and then divide this by c over here. Well, this is very similar to the equation we had for the series circuit, except that this term here was R Thevenin over L. So if we assume a form of the solution like we did before for the current, now for the voltage, say A e to the st, then we can plug it in over here as A e to the st. We could differentiate it once, which would be AS e to the st. So here's that term. And then if we take this derivative twice, we're going to have AS e to the st from the first derivative, and then another S e to the st, so we'll get an S squared. So I can pull out an A e to the st, we'll have S squared, 1 over R Thevenin C, and 1 over LC. And again, this looks very much like what we did for the series circuit, where again, 1 over R Thevenin C is being replaced by our R Thevenin over L. And so we found that this had two roots. We'd have the same two roots again, except now our term for alpha is going to be 1 over 2 R Thevenin C instead of R Thevenin over 2L. And this term is still the same here, so it's 1 over the square root of LC. Compare with our series results. This is on page 52. So we'd have three cases where alpha is greater than omega naught, alpha is equal to omega naught, and alpha is less than omega naught. So the overdamped case is where alpha was greater than omega naught, and we'd assumed this solution before for the current. We'll now do it for the voltage. And again, plugging in t equals 0, I get A1 plus A2. I have two unknowns here, so I need a second condition. Take the derivative of voltage with respect to time, but that's related to the capacitor current divided by the capacitance. And if we do this at t equals 0 plus, that would be the current in the capacitance at 0 plus. But this can change instantaneously. This is hooked up to things that don't change instantaneously, so we're going to go back and solve for this. As we had found before with the series case, this was equal to A1s plus A2s. This stays the same, this stays the same, and this stays the same as before, except that we're solving for a voltage now instead of a current. And we got an S1 and S2, which is minus alpha plus or minus the square root of alpha squared minus omega naught squared, but now alpha is 1 over 2 R Thevenin times C. For the critically damped case, we had this as our form of the solution. It was some A1t e to the minus alpha t plus A2 e to the minus alpha t. We found that the initial value is just equal to A2, and we're plugging in t equals 0 because this term drops out. Took the derivative of this expression and evaluated at 0 plus and found that it was equal to A1 minus alpha A2. So same as the series case, but now we're just doing this in terms of the derivative of the voltage instead of the derivative of the current. Lastly, for the underdamped case, where alpha is less than omega naught, have the same form of the solution. Plugging in t equals 0, we have C1 cosine of 0 plus theta. We differentiated that and set it equal to 0. We found this for the derivative of current for the series case, and then now this is the derivative of voltage. The methods and things are the same. What's different here is you have to solve for this initial condition of voltage in terms of the current. So let's go back to the previous page and let's actually solve for that. So the current leaving the node would equal the current that enters the node. Let's make these two enter. I sub c of 0 plus is equal to minus the current in this direction, which would be V of 0 plus divided by R Thevenin, and then minus I sub L 0 plus. Voltage here is the voltage across the capacitance, and so that has to also be the same as the value at 0 minus. And likewise here for the inductor current, it cannot jump instantaneously. So the value of this current at 0 plus is related to the initial condition of the capacitor voltage and the initial value of the current in the inductance. Then we use that by dividing that by C. That would be the value here. And we would then solve for A1 and A2 like we did previously. This is how you would solve for natural response of a parallel RLC circuit.